So hello everyone, good afternoon. So we are here with you today to talk about Golang, WebAssembly, and how Bazel is helping to build Go apps and Wasm apps. So yeah, the agenda for today will be this. So we'll talk about Wasm, what is Wasm, and how Golang, Wasm support is there in Golang. And then we'll go to challenges we face in Golang and Wasm, and how Bazel will solve these challenges. Also, we'll cover advantage of Bazel builds over the native Golang build, and if someone is using Go build, how they can migrate to start using Bazel to build the Go apps and Wasm apps. And at end, we'll discuss more about future of Go and what are the proposals has been discussed in Golang community related to Wasm and how Bazel helps this. Yeah, so a bit about myself. So I'm Rajiv, working as software engineer at AP Moller Maersk, the logistic company, at level 3 engineer. I'm part of platform engineering team based in Bangalore, India. So I work in backend Golang, building microservices and infra-related stuff. Which basically supports Maersk global shipping operations. So I graduated in 2022 from JSS College, Bangalore. And I'm an open source enthusiast. I did a couple of programs, summer of code, mentorship and all with gRPC Gateway organization and Captain. And for past 3 years, I've been mentoring for GShock with Jenkins org. And previously, I worked with some companies, Lumo, Redbus, Economize, and I'm here today with Naman. Would you like to tell a speak about yourself, Naman?
Yeah, so hi everyone. My name is Naman Lakhwani, and I work as a software developer at Allen Digital. I am also from India, and previously I worked at companies like VMware and Nirmata. I was a Kubernetes 1.26 and 1.30 release shadow. And during my university days, I was also a Google Summer of Code and Linux Foundation mentee with the Kubernetes project. So today, Rajiv and I will walk you through the journey of building production-grade WebAssembly applications with Go and Bazel. So over to you, Rajiv.
Yeah, thank you, Naman. So let's start with what is WebAssembly. So basically, Wasm began as a browser tech and basically it is designed to run high-performance application, so which we cannot run in web browsers. So we can, via Wasm, we can run those application within the web pages. And so in a nutshell, it defined as sort of like binary instruction code for a stack-based virtual machine. So those virtual machine will have a stack-based memory. And also it often referred as a host or a runtime. So at its core, Wasm provides like compute and memory operations. However, a host environment like browser and runtimes can basically using the browser and runtime, we can extend the capabilities and provide facilities out of the browser. Over time, Wasm has been grown beyond the browser. So we have different runtimes like Was0, Wasm time, Wasmer. So these are the runtimes developed by the different companies to run Wasm application out of the browser, which we can serve as Wasm modules on servers, desktop, and even on the embedded systems. So how it works is like these runtime can compile Wasm programs directly embedded within the existing applications. So for example, a plugin written in a Rust can compile to Wasm and embedded in a Go application. So basically it works like a shared library with a sort of like stronger isolation using Wasm. And this is the biggest strength of Wasm, like a sandboxing. So it enforces a memory and capability isolations and making it more safer to run untrusted models. So this is all about Wasm. And we have like Go Wasm import and Go Wasm export. So if you want to import some function out of Wasm models, so we can use this Go Wasm import. And if you want to send any of the function out of the Wasm models, you can use this Go Wasm export feature, which comes in the Golang Wasm support. Yeah, so let's talk about how Go support Wasm, like how many ports and how it developed. So basically, WebAssembly support was first published in Go 1.1 back in 2018. So at starting, it has started with a JS port. So like it's allowed compiling Go programs to run inside web browser using JS-based WebAssembly runtime. And at that time, Go Wasm target was mainly browser focused. So basically depend heavily on JS side input output. And over the years, contributors have worked expand the support beyond the browsers. So in Go 1.21 release in 2023, we have a new port called WASI P1, which is called WASI Preview 1 port. So this is a new compilation target was added, like Go OS WASI P1. And this support something called WebAssembly system interface, which is known as WASI. And how it helps is like it enables Go programs to run in a standalone Wasm runtimes. We discussed earlier like V0 Wasm time, so even without needing a browser. So yeah, I mean, in early 2023, Go community and WebAssembly community has worked to maintain and improve the Go assembly support. And yeah, I mean, the transition from Go 1.1 and Go 1.2 took almost like 5 years to, and this all was largely driven by the community and people who contribute to those projects. So today, ongoing work focuses on the component model. So in WebAssembly, there is a new preview 2 component model, and that support has to be added in Golang in future releases. And the advantage of this is like has like better host interoperability, aligning with Go runtime models and network support. And yeah, I mean, together these efforts make Go a strong choice for building fast and portable like sandbox application with WebAssembly. I will hand over to Naman, who will discuss more about the challenges we face building these Golang apps with WebAssembly. Over to you, Naman.
There are certain challenges we face with Go and WebAssembly. So while Go provides native support for compiling to WebAssembly, the build process often suffers from reproducibility and dependency issues, which we all know. But by default, the Go toolchain does not guarantee hermetic builds. Several factors from the local system can influence the output, including the environment variables, network issues, and the system state. A key example for this is the use of environment variables, which we set in Go environment, including Go path and Go mode cache, which are local to each developer's machine and can lead to different module versions or cache dependencies being used across builds. So due to this, developers experience certain outputs across machines or operating systems because traditional Go builds depend on the local environment, the Go toolchain, caches, and the network access. So rebuilding large Go projects for WebAssembly can also be slow because the Go toolchain lacks the fine-grained caching and parallel execution for the Wasm targets. So integrating Go Wasm builds into the CI/CD pipelines can be difficult because each environment might produce different artifacts, binary artifacts, and the expected output might differ. So these challenges are where Bazel makes a difference by enabling hermetic, reproducible, and cache-efficient builds for Go to Wasm workflows. So let's see how Bazel helps and provides a solution for the problems and challenges we just saw. So Bazel directly addresses these challenges by enforcing hermeticity. So its sandbox build environment ensures that that only declared inputs are used with no access to your local environment variables like Go path or Go met cache. So this guarantees identical Wasm binaries on any machine or on any remote environment. So Bazel introduces advanced local and remote caching. So if a dependency or any part of your code has already been built by you or by any of your colleague or teammate, it is fetched from the cache rather than rebuilt everything from the base. So this saves a significant amount of time, right? So these caching and hermetic properties together provide true reproducibility, which is especially important for WebAssembly because it takes a lot of time to build from the source code every time. So you can be confident that Wasm binary deployed to the production is byte by byte the same which you built locally. So Bazel analyzes the entire dependency graph of a project, allowing it to execute independent build steps in parallel. So it rebuilds only what has changed in your particular file and resulting in very highly efficient incremental builds. So this ultimately creates a stable and reliable CI/CD pipeline, right? The same commands that run locally also run in the CI, and the expected output is also the same with the remote caching and consistent, predictable outputs. So there are certain challenges of Bazel builds over Go build. So one is like Bazel extends far beyond the capabilities of Go build, right? While Go build focuses on simplicity and speed for local development, Bazel focuses on scalability, reproducibility, and cross-language integration. Like say you have backend in Golang, front-end in TypeScript. So Bazel helps you like build everything in the one. So its hermetic and sandboxed approach ensures that every build which you do on any machine is identical regardless of the system it runs on. Also, the Bazel's fine-grained action graph enables more parallelism and faster rebuilds, especially in larger projects. In short, if we see, Bazel transforms Go's build process from local and environment-dependent builds to global and more deterministic production-grade environments. So let's say someone has a Go project and they've used Go build. So how can they migrate from using Go build to Bazel build? So there are basically three important files for the migration. One is module.bazel, another is build.bazel, and third is min.go, where your main core application logic lies. So module.bazel tells like Bazel what Go version to use and downloads that particular version during the build time. And the build.bazel defines how to build your code for native and WebAssembly. And your go.mod file remains the same. There are no changes in that. So let's see each of these files in let's see this a snapshot of these files, and let's see how we write this. So let's say there is a module.bazel file, for example. So there are certain sections in this file. One is module. Then we have Bazel dependencies, Go SDK setup, and the Go dependencies. So this file basically configures Bazel to use Go and defines all the dependencies and extensions needed for that particular build. So the module line in the starting simply gives your Bazel project an identity, the name and the version you are building for. Next, we declare the Bazel dependencies. Here we define the rules Go and the version. Also, here we are, so rules Go is nothing but a Bazel rule set that actually teaches Bazel how to build the Go code. Without it, Bazel wouldn't know how to compile .go files and generate the Go binaries. Another dependency we are adding here is Bazel. So this is a Bazel extension code generator for Golang. And it automatically analyzes your Go source and your go.mod file that then generates or updates build.bazel file. So that means you don't have to manually define every source file. Bazel keeps things in sync automatically. Then next we have Go SDK setup. So here, if you see, we are defining on the line 12th, we are defining the actual Golang version we are trying to use, so that so we are basically pinning that particular version so that it can run on anyone's machine. And there are no dependency issues on that particular Golang version. Finally, the Go dependencies section connects Bazel to your go.mod file. It means like the Bazel and Go mod stay in sync. Both use the same dependency graph. And at the last, on the line 17th, if you see, this line makes those dependencies available for your build projects, build targets. So in short, if you see, this file makes Bazel fully aware of your Go environment, and it defines the toolchain imports for your dependencies and guarantees everyone uses the same setup. Like if you see, we are defining the particular rules Go version, Bazel version, Golang version. So there are no dependencies issues at the end, and this makes the builds reproducible, consistent, and easy to share and build at any environment, be it local or remote setup. So let's see the another file, build.bazel, and Rajiv will walk you through this file. So over to you, Rajiv.
Thank you, Naman. Let's talk about the build.bazel, the second file. So what it means. So the file defines how Bazel should build a Go project. So basically sort of like a recipe, what to take input, output, and like what for which platform. So you can see the file like instead of running Go build manually, Bazel handles everything with clear build rules. And so basically first we compile the main.go into a Go library target, and this is not executable, so you can reuse the unit of code. So you can see we are embedding the same library in both the native and Wasm binaries at line 18 and the line 11. So this makes build faster and consistent, and there is no sort of like a duplicate work we are doing here. So we have defined the two binary targets. One we are defining for Go build, and other we are defining for the Wasm thing. Second builds for WebAssembly, so a .wasm file that can run in a browser or WASI runtime. So we can run this Wasm via runtimes or via browser. So the native library is just like a running Go build. So how we run Go build, it's like same. It works like same on your machine. And Bazel detects your OS and architecture automatically. So it outputs an executable you can run directly. And the Wasm binary is a cross compilation. So we set Go OS equal WASI P1 to target the WASI environment in Golang. And you can see the Go arc equal Wasm to compile for WebAssembly architecture. Basically, this produces a .wasm file that can run in a sandbox environment like browser or any of the runtimes. And finally, at end, you can see the gen rule to rename the output. So basically, Bazel internal output path can be long and hashed, and the general copies it to clean, predictable name. Like here, we have named it like app.wasm. So that makes it easier to swap, test, and share the build's results. And overall, yeah, Bazel gives a sort of reproducible and hermetic builds, and every build is cached, isolated, and sort of like deterministic behavior, so produce identical output at any machine. The same Go source can now target multiple platforms, so whether it's a native or WebAssembly, a single configuration will work fine for everything. And this is the main source code. So for example, we have given a main.go, so we don't need to change anything in the business logic or Go file. It works fine when we are doing migration from Go build to Bazel. So here you can see the output. So when you run as so it will show different values when built for a native versus Wasm. And yeah, so basically you just need to write once and for multiple platform, and it will work fine. Yeah, so how we can run this? So we need to build first, and you can see run native. So when you run native, so it runs Go build, and when we need to run with Wasm, we need a runtime. So here we are using a Wasm time. So native binary shows your actual OS and architecture, so ARM64, and Wasm binary shows the WASI P1 and the Wasm. So basically same code, different platform. So we can use here. So yeah, so the next slide is like about the future of Go and WebAssembly with Bazel. So let us look at where Go and WebAssembly stand today and how Bazel strengthens this ecosystem. So several major improvements in Go WebAssembly support have been already landed. So there are some proposals like Go Wasm export, Go Arc Wasm 32. So with Bazel-based builds, we are moving towards more even reproducible and high-performance Wasm toolchains. So the Go Wasm export compiler directive was introduced in Go 1.24, and basically what it does is like it allows a Go function to export it into Wasm modules. And Go Arc Wasm 32 proposal was like adding a 32-bit pointer and integer support. So basically it's more bringing Go Wasm target closer to capabilities of Wasm hosts. And work is also underway on WASI port. So as we discussed component model, so there is some discussion going on having how we can add WASI preview to the Golang, like how we can tweak the scheduler because Golang has a like high size, big size scheduler and runtime stuff, and component model makes like small modules and all. So there should be an improvement, maybe Go team side. And on the Bazel side, I mean, integrating these new Go and Wasm features with Bazel like will help us to have a Hermetic build system, like to provide more cache efficient and workflows which are more parallelized. And yeah, I mean, together Go is advancing a Wasm support and Bazel reliable build guarantee make it like sort of like more possible to build a high performance, portable and maintainable Wasm application at high scale. So yeah, that's a wrap, and these are the references. You can go through it. The slides you can find here, and the links for WebAssembly and this thing. And you can also scan the QR to go through the repo link. And yeah, thank you so much for listening to us. And we are open for the questions.